Hello, my name is Eric Hoffander, and I'm a graduate student in electrical engineering at Colorado State University. I'm presenting on a project for embedded machine learning, where I detect water use via deep learning combined with a sensor phase delay. This project was started by my electrical home devices being so much more intelligent than my smart water meter. The best-in-class electrical smart systems like Sense or Span are far more advanced than FIN, the best home water monitor. Smart panels have multiple voltage and current sensors that allow them to see both the active and reactive power, generating a unique profile for every device in my house. Water meters only have a single unit, mounted on one pipe, meaning every device will generate an identical pressure and flow rate, meaning we can never distinguish between two sinks in different bathrooms. Electrical and hydraulic circuits are often compared, as there are many physical similarities: voltage with pressure, inductance with momentum, and current with flow rate. The problem is that every faucet has an identical path to the current detector. As it doesn't know the length to each device, it cannot distinguish between them. If we have multiple sensors located a different distance away from each other on different paths, every event should have a unique profile based on the different acoustic path from each device to the sensors, as well as the difference in the momentum of the water. Putting this into practice was harder than first thought. The initial training was all done in Python, based on simple air acoustic models. However, the speed of sound in water is 1,500 meters per second, meaning I only had a 3 millisecond window to gather all of my phase data between my two sensors. Below you see a raw recording of two sensors to my sink turning on. The first order decaying pressure wave is visible, but is drowned in digitization noise. Even worse, the timing is broken, as we have random delays between every sample up to 1 millisecond. We can't drive the data collection directly via USB due to polling errors. We need the device to record data in real time and return the data to us asynchronously. To fix this, I developed a triple-core processor, one ESP32 for machine learning, an RA ARM chip for the ADC, and a micro real-time clock for data timing. I created a dual-channel rolling FIFO with a variable trigger to capture both before and after the first pressure wave was seen by any sensor. I then took a day walking around my house, turning on and off every faucet dozens of times to generate labeled training data. This training data was saved to an onboard SD card as well as piped to a socket to my host PC. The real-time data is now accurate to the microsecond, giving me more than 1,000 times the time stability of the USB. The 10-bit ADC is oversampled 10 times, giving me a 14-bit average, which fixes nearly all of the digitization noise. Now, an IoT water meter isn't an LLM. The power and bill of materials budget means that we need to spend basically nothing on the processor. To this end, I designed the model 4 times, each in decreasing layers of complexity. The Edge Compute Coral Dev is capable of both training and running the model, but still has a power and money budget more than 10 times higher than my goal. The Raspberry Pi is again limited by the lack of a dedicated ADC, meaning additional hardware is required. The ESP32 was the ideal device, but it requires serious optimizations once our model is designed. Passing the labeled raw data to the RN and acoustic model showed terrible results. No matter how I set up the super parameters, we simply did not have enough data to let the model learn anything interesting, without any baseline knowledge. The pressure deltas drown out any information, and the model is only able to linearly distinguish between each faucet based on how much I opened the valve. This was not a good path. So instead of passing the model the raw data from our system, we pass it the phase and frequency of the FFT at each step. This is called a wavelet. These wavelets show unique patterns for every faucet, enabled a 2D convolution model and a dense model to instantly jump from chance to 100% accuracy in 4 epochs. Even by eye, we are now able to distinguish events more easily in this view. Awesome, we have a 100% accurate model. All's done, right? No. No one besides NVIDIA investors want a 3080 GPU just to tell them when they flush a toilet. The current model requires 2.8 megabytes to store the weights and consumes 80 megabytes of RAM. We have 1 megabyte of storage and 512 kilobytes of RAM. We need to radically reduce our model size. Step 1 is to rip up the model to find out what layers are allowable. The embedded model has a radically reduced operations subset. Next, we need to reduce the wavelets amplification of our data by a factor of 32. Next, we need to remove all the double precision inputs and weights and move to a fixed Q8 model. Next, we'll drop out every weight that has little impact. We can combine all of these steps, and we're able to reduce our weights from 2.8 megabytes to less than 60 kilobytes. At each step, we need to reapply the quantization-aware training just to make sure that we're not losing our high accuracy by minimizing our model. On the far right, we see the model is deployed to our device. It takes in values, converts them to fixed point, and performs a 1D convolution before passing to dropout and dense fully connected layers. To the left of it, you see the model as first designed. The changes between them were large as the embedded IDE did not support many of the operations in the normal TensorFlow model. Originally, I wasn't really aware of what was and what wasn't a custom op, so slowly climbing through every layer taught me a lot about how the machine learning models actually work at the C layer. Finally, here is a quick demo of the model running.
This is a demo for 528 machine learning. This is a demo for 528 machine learning. First, it's going to go into an averaging. It's going to find the difference in the head pressure between the two units. Now the trigger is armed. Now, since I don't want to walk upstairs, we're going to do the ball valve. Should detect an event. Pass to the system. And we detected the event. Now it's recorded. It should go back now and arm itself. Now we're rearmed.
Thank you for taking time to watch the presentation. If you're interested in the models directly or a paper going over this topic, feel free to contact me. Thank you.